Hi everyone. We are still in our section on descriptive statistics, and we are studying quantitative data in this video. More specifically, we will bring our attention to measures of position. In the past, we've discussed the median as being a measure of central tendency, but it also happens to be a measure of position. In fact, it's the value that separates the 50 lowest values, or the 50% of lowest values, from the 50% greatest values. Other measures of position are vastly used to describe the distribution of data. In particular, we'll focus our attention on percentiles. We use P sub k to represent the kth percentile of the data. Calculating a specific percentile may depend on the type of data that we are dealing with. Now, for percentiles between the 1st percentile and 99th percentile, the kth percentile of a distribution is roughly a value that splits the data into the lowest k% of the data from the 100 minus k% higher observations. Excel has integrated functions to calculate any percentile from a data file. Whether you're using a French or an English version of Excel, you'll find under percentile or centile the options that you'll need. Some sub-options will ask you to include or exclude the percentiles, and that will not be much of a concern to us. More often than not, we're going to be calculating a percentile from a frequency table. Now, in the case of discrete quantitative data, the kth percentile is the value whose cumulative relative frequency is the first to exceed k%. There is an exception, though. If a value's cumulative relative frequency is exactly k%, then we will deem that the kth percentile is located between this value and the next one. We're going to show examples to illustrate how this is applied. In this example, we have the distribution for the number of children per household. Values go from 0 to 6, and the data is discrete. So given the frequency table, find the 20th, 40th, 60th, and 80th percentile. Well, the first value, whose cumulative relative frequency exceeds 20%, is x equals 1. Therefore, the 20th percentile is 1. Likewise, the other percentiles are found. The first observation, whose cumulative relative frequency exceeds 40%, is also x equals 1, and therefore P40 is 1. The first value of x to exceed, whose cumulative relative frequency exceeds 60%, is 2. As you can see, the cumulative relative frequency is 76.2% by the end of that observation. So P60 is 2, and the first observation whose cumulative relative frequency surpasses 80% is 3, and therefore P80 is 3. Here's an example where we're going to have to be a little bit careful because of a curveball we'll encounter along the way. In this table, we have the frequency for the family size, so the number of people who actually inhabit a given household. Numbers go from 1 to 6, and again represents discrete quantitative data. We're going to find the median, the 30th, and 70th percentile. The first value, whose cumulative relative frequency exceeds 50%, is x equals 3. Therefore, the 50th percentile, or the median, is 3. When looking for the 30th percentile, we'll observe that the first value, whose cumulative relative frequency exceeds 30%, is x equals 2, and therefore the 30th percentile is 2. This time, however, none of the values are the first to exceed specifically 70%. We have reached the exact cumulative relative frequency of 70% when x is 4. So P70 should be chosen between 4 and 5. Now, any number between 4 and 5 can act as the 70th percentile. But strangely enough, the tradition is to choose the number that is 30% of the distance to the next number, 30% being the complement of the 70%. So if we had been looking for, let's say, the 80th percentile, we would have gotten 20% of the way to the next number. So these are things we'll apply in class. When data is grouped, then we will not be able to find exact values for the percentile because we have lost the individual information. A process of interpolation will have to be used to estimate the position of a given percentile. Here's the percentile formula for grouped data. So pk is the percentile, the kth percentile we're looking for. Lowercase fk is the relative frequency of the class that contains the kth percentile. Wk is the width of the class that contains the kth percentile. Lk is the left hand or the lower bound of the class that contains the kth percentile. And uppercase fk minus 1 is the cumulative relative frequency up till the preceding class. So let's apply this formula in an applied setting. So here is data that is continuous and has been grouped. So we have the distribution of salaries that we put into 5 different classes of size 20,000. From the data, we're going to find the 40th and 80th percentile. So let's recall our formula that I have highlighted at the bottom. When looking for the 40th percentile, we'll notice that the first moment when the cumulative relative frequency surpasses 40 is at the end of the second group. So the 40th percentile has to be somewhere between 20 and 40,000. Therefore, the left bound of the class where the 40th percentile is found is 20. So I've made the numbers a little bit cuter by just avoiding to write the thousands. So 20 is the left bound of the group inside of which we find the 40th percentile. The formula says we need to do k minus f of k minus 1. Well, k is the percentile we're looking for, so 0.40 or 40%. The previous group had compiled 10.2% or 0.102%, not percent, decimal, of the observation. So we're going to try to fetch that 29.8% that is missing to achieve the 40th percentile. All this in a group that contains 35.5% of observations. So the relative frequency of the second group is 0.355, that's our divider. And the width of the class is 20. In the end, we'll get 36,779 as the estimated 40th percentile. When looking for the 80th percentile, we're going to have to look a little bit lower because the first moment when the cumulative relative frequency exceeds 80 occurs by the time we end the fourth class. So in the fourth group, the left bound is 60 or 60,000. 80% is the percentile we're looking for, so 0.80. We had cumulated 0.722, so 72.2% of observations by the end of the previous class. So we're missing the 7.8% to fill in that gap. And that tells us that proportionally, those 7.8% are found within the 19.6% that the fourth group has. That's why it's our divider. We're going proportionally. All that times 20, 20 being the width of the interval. So 65,887 would be our estimated 80th percentile. Quartiles are also measures of position. Quartiles are in fact just special cases of percentiles. So the 25th percentile is often referred to as the first quartile, and we denote it by Q1. The 75th percentile is known as the third quartile and is denoted as Q3. The 50th percentile is also known as the median and could have been called the second quartile, but really the median is the traditional name we'll give to it. Quartiles can be calculated using the kth percentile formula that we presented in the previous slides. The min and the max are also measures of position, as they reveal the extreme values that have been observed in a population or in a sample. Excel has integrated functions for you to find the min and the max, and as you would guess, they are just called the min and max functions. Now, the best way to present data graphically and take into account the measures of position are called box plots. So it's a convenient way to visualize the variable's distribution, and it provides information about the first and third quartiles, as well as the median in what we'll call our central box. Lines extend from the central box, and these are called whiskers, and at the extremity of the box, we will find indicators of the extreme values. Now, generally speaking, whiskers will end at the min and the max values of the variable. But more and more, the following type of box plot is used. Whiskers will end at the min and the max unless these values are more than 1.5 times the interquartile range from the nearest quartile. Any value beyond these limits are highlighted by stars and are considered as outliers or extreme values. So let's see how that shows up graphically. Here's an example where we have variable x, whose first quartile is 40, whose third quartile is 60. So that means that the interquartile range, the separation between those two quartiles, is 20, and 1.5 times that is 30. The variables min and max are 20 and 100 respectively, and the median is 45. So graphically, here is what the box plot would look like. In this case, I've drawn the whiskers at the min and the max. So notice how the extended lines have at the extremities 20 on the left and 100 on the right. Those are the min and the max. And then there is a central box representation where 40 and 60 are the extremities of the box. Those are the first and third quartiles. And somewhere within the box is the median, located at 45. That's the vertical separator in the middle. Not in the middle, a little bit slightly to the left. In fact, that's what the graph shows, that the distribution is not perfectly symmetric. Notice how the median is not symmetrically placed, and the extensions go further to the right. So this is a skewed distribution. Here is the second way of presenting box plots, where whiskers are not allowed to go further than 1.5 times the interquartile range from the nearest quartile. Okay, so this time you see that there is no effect on the central box, which has Q1, Q3 at 40 and 60. The median is still located at 45. To the left, the whisker extends all the way to 20, which happens to be the mean. And to the right, the whisker is blocked before eventually showing some stars. So here's what's happening. The whiskers cannot go further than 1.5 times the interquartile range. So from the third quartile, we added 1.5 times 20, and we blocked at 90 the whiskers themselves. All the data that was above 90 is represented with the stars. In this case, there would be 3 outliers. On the left, from the first quartile, we subtracted, so we moved leftwards 1.5 times the interquartile range, but no values go that far. So there are no stars at all at the left.